I think yesterday you had a session on VLMs, and today we are going to learn a little bit about fine-tuning LLMs, which is, I think, overall umbrella of large language models, and VLMs are also a part of them. So yeah, let's start. So first we'll cover the code first basics of LLMs, which means that in just a few lines of code, I'll try to give you the entire overview of how an LLM looks like, and then we will go through Unsloth notebook. Unsloth is a library. I think it was introduced in yesterday's session as well. And we will see how to use that to fine tune on our custom dataset. Okay. So yeah, I'm just pausing so that everybody can settle. Okay. So we'll try to go very slow over this particular part where I'll try to cover the basics of LLMs, and I would like you to ask as many, because we are trying to cover a lot of things in just a few lines of code. So let's get started. So basically we know that LLMs, they basically work on text, right? And we have the textual data. We try to divide them into different tokens and try to process them. In the initial times when the research was going on, what were the like the famous tasks which were going on in the language domain? One was the language translation, right? You want to translate from one language to other. One was fill in the blanks, question answer, sentiment classification, right? These are the kind of tasks which were like people were doing research on them. So let's see how do we process these things in the LLMs. But before I go there, let's also try to do a small recap of like what technology existed before LLMs to do the language processing. Any answers, any comments? What models did we use before LLMs? RNN, yes. LSTM, GRU, sequence to sequence models, right? These are all the technologies which existed before transformers came into picture. And what was that fundamental thing came up with which made it famous? Attention mechanism, right? And what is so specific and so nice, so generalized about the attention mechanism? Can anyone say? Yes, that is one, that each and every word can attend to each and every other word. And what benefit does that bring? Okay, but we could do that earlier also. Like that was possible in earlier models also. But what specific thing, this attention mechanism? Yeah, I think that's similar to what he said. So the best thing that attention mechanism came up with is parallelization, right? Because one of the key challenge in RNN and LSTM like models was that you had to do that sequentially. If you had to attend to the previous, right? So using transformers and with attention mechanism, we can attend to everything all at once. That was one key benefit, and there is one more key benefit, if anyone can name. You can think of the language translation problem. Like what is the key challenge there? Like when you are trying to translate one language to other, it's not necessary that the number of input tokens will stay constant or the output tokens will stay constant, or even like even if there would be some relation between the number of tokens between two languages. Not necessary, right? It's possible that there is a single word in one language which the other language may take 10 tokens to represent. Right? That's quite possible. You have dynamic input and you have this dynamic output. You want to handle that automatically without making architecture level changes in your model, right? So LLMs or the transformer mechanism also allowed that, and we will see how that becomes possible, right? So let's pay attention to the second line here, which says tokens equal to I play cricket every day. Now, if you pay attention, I have broken this entire sentence in a very specific way. I have kept I play as together, and they are not treated as tokens. Can anyone say why we would like to do that? Yeah. Can you be slightly louder? That's not the reason why we would like to keep like I and play together. Like we are treating that as a single token here. So you are saying that if I treat them separately, they are not having in. Okay, but we are not looking at the relations just yet. We are just doing the tokenization, which means how to represent text into computer language, which means in numbers, right? So to do that, we have to first break the entire sentence into tokens. Yeah. Yes, right. So that is coming closer to why we are doing this. So just to give you a perspective, how tokenization happens in nowadays LLMs, which you might have heard of as GPT, Llama and all. Like earlier, they were using heuristic methods to do the tokenization. For example, if there is an ing, you would try to break it using deterministic formulas, right? That like if there is a playing, then play should be different and then root should be different and then ing should be treated differently. But then people found that this choice was made by humans, right? And it did not lead to superior performance. So can we use the data itself to do this breaking of tokens for us? And that's where this kind of tokenization came into picture, that they tried to check the frequency of different phrases at different lengths in their text, right? Because the llama-like models, they were trained on a huge data set, millions and billions of tokens. Right? So they tried to analyze the frequency, and that's where we can see that which words will be broken and which phrases can also come together. Right? If you want to play with something like this, you can go to this website. You can just Google like OpenAI tokenizer and something like this would come up. So just so that you can see, yeah. So here I have written, I enjoy soda with khaman dokla, right? Everybody knows khaman dokla. It's a Gujarati thing, okay? So as you can see here, every color breaking here is representing a different token. It says that we have 31 characters and 9 tokens. I is treated as a separate token. Enjoy is a separate token. Even soda is a separate token. But you can see that khaman dokla is broken into multiple tokens. That is because when this model was trained, khaman and dokla words were not present in that frequency. So they then tried to divide it into multiple chunks, and then each of the chunk was used as a token. So here KH is a token, AMAN is a token, DH, OK, LA, all of them are separate tokens, right? So when you are trying to build a big model, trying to pre-train on a billions of tokens, you can use this kind of smart tokenization so that you don't have to rely on the human-made heuristics. Another example of the same is everyday, right? Generally, we write everyday as a one word, but here I have broken. So it's possible that in your data, everyday is not appearing so frequently. So you would like to break it into 2 different tokens. Right? Somehow this results into better performance in LLMs. Okay. Now let us see how do we represent this in before like passing into the LLMs. So each of this token is assigned a particular integer value. Let us say we assign 10350 to iPlay, then to cricket 2045 and so on. So before we start training the model, we have to set a particular vocabulary size here. For llama models, the vocabulary size is 128256. So this is the maximum number of tokens that llama model can handle, right? And now you would appreciate that why this dynamic chunking for tokenization is helping us, because we don't have to now really represent each word in the universe. If that word cannot be fitted into your vocabulary, you just break it down. Then you are sure that each of those chunks are going to be in the vocabulary. In the worst case, you would divide into two characters, right? So each of those characters are going to be in the vocabulary anyway. So that's why they were able to restrict the vocabulary size to something like this number. So all of these integers has to be smaller than this vocabulary size. And this is like decided when the data was pre-processed, and then we have a fixed number assigned to each of these words or tokens. Then comes the embedding layer, where we have a lookup table where each of these token IDs are mapped to a 2048 sized vector, and here the 2048 size is called as the model size. You might have heard that in different LLMs you have different model size, and you will see that in the entire architecture you will see this number repeatedly. Okay, so here we have 4 different tokens. So our embedded tokens will become 4,2048. So each of this word or each of this token is represented as 2048 sized vector. Initially this vectorization happens randomly. So if we try to draw an analogy between the classical machine learning, let us say you have some tabular data of x and y, you are trying to train your model. Do you ever back propagate through your inputs, which is x? We don't do that, right? We only back propagate through weights, and we try to train the weights so that x to y mapping is happening correctly. But in LLMs, what is happening is you want to assign a x which is 2048 sized, which we call as features, right, to each of the tokens, and then you train those embeddings as well, those feature representations as well, as your pre-training goes on. This happens only during the pre-training. When you want to do the fine-tuning, you don't touch this. You freeze this and you only try to modify other layers. Okay, so any doubts till this point? Any questions? Okay, so let's go forward. So till this part, we have converted the tokens to a feature vector. Now comes the next part, which is the attention. Attention layer is that we have these 3 weight matrices. Like, you don't need to really go into the terminologies of like why something is called as query, key, values. Just think of this as 3 different weight matrices, which are of square size 2048 by 2048, and then you multiply this feature representation with each of these weights to get query, key and value. And because this is a square matrix, when you multiply it, it's 4 cross 2048 multiplied by 2048 cross 2048. So finally you will get the same shape. So you will see that in the entire LLM architecture, we will try to preserve this shape as it is, 4,2048, right? So now, out of this single representation vector, we have created 3 different representations called query, key and value. Okay, now comes the attention. In attention, what do we do is, we multiply the queries with keys. So each of these queries are multiplied with the keys, and then we divide by the square root of the model size, and here model size is 2048. Okay, then we apply the softmax on the last dimension, which would make the summation of the values to 1, and then we multiply that with the value matrix. So here finally we will again get the 4,2048 sized vector, right? So the beauty here is that when you try to like get a dynamic sized inputs in query, key and value, you will be able to do that. So how do we do that is, in query, you can have a different shape. Let us say here you have 4, but you might have 8, 10, 12, anything. And in the key and value, you can have the same dimension, which would be, let us say, 4. And this architecture won't change, right? This will still work out, and we will get the residue of size, which would be similar to the size of Q. Okay, so anybody can say like why we are calling it as a residue here? Do you know about resonates? Right, so what unique thing that resonates came up with? That's the residual connection, right? The intuition behind residual connection is that when you are trying to transform a feature vector, instead of transforming it completely, maybe it is better to just learn the differences, right? You learn a difference vector and then add it to the existing vector so that it is perturbated a little bit. So that difference is easier to learn than directly modifying the entire vector. And that led to a significantly better performance. Ideas was also used into the LLMs. Once we compute this residue, we simply add it to the embedded tokens, which is our feature representation, and get an updated representation 4,2048. Right? So till this point, we have completed the forward pass over the attention layer. In the next part, we have a dense layer. In the dense layer, what happens is that we want to project this model dimension into a high dimensional space and then bring it back. So that's all which is happening in the dense layer, which follows the attention layer. Here we have gone from 2048 to 8192, and then we come back from 8192 to 2048. Once we do the up projection, we apply the activation function. Here I am using ReLU, but over time different activation functions were used in different LLMs. Then we get this down projection again, which is of size 2,2048. Again, this is also a residue. So we are not directly modifying the feature vector, but we will just add that difference or residue to the existing feature vectors, which will again be 4,2048. Okay. So this makes a single layer in the transformer architecture. First is the attention layer, it follows by the dense layer. There are two more layers which we have not talked about here. One is the normalization. There are different kinds of normalizations which are used right now. And the other one is positional encoding, which means that you have to somehow encode that which word is first and which is coming later. Because in the attention mechanism, there is no such provision which can tell you that which word came first and which came later. So we have to somehow encode it, and like that's considered as some like you can look at that later. Okay, so we can have more than one transformer layer in an LLM. This attention layer plus dense layer makes a single layer, and then let us say you have 10 to 15 such layers stacked one after the other, and at the end we have this LM head, which projects this 2048 sized vector to the vocabulary size. So here I have just taken a random number of 10,000, but this number should exactly match with your vocabulary size. So you just simply multiply this with the weight matrix and you get logits of shape 4, vocabulary size. And then the typical classification happens, right? In the classification also, what do? You try to predict a vector which is of size of number of classes. Once you have that, you try to take argmax and then you get the next token. So till this point, like we have covered the basics of like how an LLM works, and this holds true even to the today's LLMs, which are like you see Llama models and GPT models. All of them use this exact flow that I have explained just now. Okay, so till this point, are there any questions? Okay, so one thing which I have not talked about is that in the original transformer architecture, there was encoder decoder kind of things. And what we just saw is a decoder only model, which means that we are only interested in trying to predict the next token. But there is one more thing we have to ensure to make sure that this is working correctly, is that when we are trying to predict a token, the attention should not be applied to the future tokens. Otherwise, you already know the answer. Sometimes when people make this mistake, their loss goes to zero instantly, even after first or second epoch. And that is because you are already attending to the future tokens and the same token itself. To do that, people use various tricks so that you don't attend to the future tokens and only attend to the previous tokens. Okay, so I think yeah, we have covered the basics of LLM till this point. If there are any questions, we can take now. Yeah. This one, that is matrix multiplication. Yeah, you can either use torch dot or you can use this syntax. Okay, so if there are no questions, we can go towards the fine tuning of LLMs. So this notebook is basically taken directly from Unsloth's documentation, and I have made some modifications to it. So even later after this lecture, if you want to look into more resources of LLM fine tuning, you can go to Unsloth, and they have nice notebooks of describing different concepts there. Okay, now coming to Unsloth, here we are loading a Llama 3.2 1 billion instruct model. So anybody knows like what's the difference between just Llama 3.2 1 billion and the instruct? Yeah. Yes, right. So the instruct variant is actually fine-tuned on the pre-trained Llama version to do the question answers. We are loading that model, and once we load it, we have the both model and tokenizer here. This is basically a PyTorch model, so that anytime when you print a PyTorch model, you will get a view like this. So this is also a good time to like recap what we saw just now in a real life model and like a latest model, right? Llama 3.2 was like just released a year back or so. And you will be surprised to see that nothing has changed much over the years in these architectures. You can see that first is the embedding layer. Here you have the vocabulary size going to 2048. Then you have 16 layers of Llama decoder layer, which consists of 4 different types of layers. One is the attention, MLP, layer norm, and post attention layer norm, and embeddings, rotary embeddings. Right? So here we see that Q, K, V, and sometimes this out projection is also used whenever there is a multi-head. At the end, we have the LM head, where we are trying to project from 2048 to vocabulary size band. So this shows that you don't have to get intimidated by the like latest LLMs that are coming, newer like LLMs are coming day by day. You can just open up any model and like you can query this model. Let me see if this is running. Okay. I would also suggest that you learn the basics of PyTorch and like how the model and parameters, all of those things we can access in a PyTorch model. These models, all of these newer models are built on the same framework that PyTorch provides. Unsloth is installed, and now model is loading. You can also not use Unsloth and do the fine tuning using other libraries like Prof. I think it was covered yesterday. right? But Unsloth just provides you better tools so that you can use like bigger models in smaller memory, and that also like even the training and inference both can happen at a faster pace if you use Unsloth. It shows a nice summary of what compute we have. In Colab, we have Tesla T4 GPUs. There is a single GPU and it has max memory of about 14 GB. So whenever you are doing inference or training, it's a good idea to keep an eye on NVIDIA SMI command to see how much memory it is consumed. Sometimes during these smaller experiments, we don't pay much attention because we never exceeded the GPU memory. But bigger models will not even fit into a single GPU. Even if you have like latest models like H200, which may have more than 80 GB of GPU RAM. Model and tokenizer are loaded. So how you can access each of these individual things is like this: model.model. It gives us a llama model. Then I can simply access embedding layer, right? So it shows me the embedding layer like this. Dot layers. This is a module list, and then I can check what is the first layer in the module list. It shows me the llama decoder layer, which has 4 different layers here. Okay, so currently the model is on CUDA. We are trying to move it to CPU just to see some things. I am trying to choose a particular token ID which is completely random, and we are trying to pass it to our embedding layer. And we see that we get a 2048 sized vector as the output. So this is a mapping between this token ID and this 2048 sized vector. Okay, we already saw these layers. Coming to the next part. So now we are going to apply LoRa adapters to this model. So anyone remembers what is LoRa from yesterday's session? Yes, that is low rank adaptation. Anybody remembers how that works? And why do we need low rank adaptation? Yes, right. And when you're trying to fine tune a bigger model, it can take a lot of compute. But if you use techniques like LoRa, you can achieve same performance without consuming that much memory and that much time. Right? So all we do in LoRa is that we try to create a low rank matrix which is of same size matrix, and you try to add it. Right? So the overall number of parameters which are trainable, they get much lesser than the overall number of parameters of your model. Sometimes it is about 1% of the total number of parameters that you have. So your training or fine tuning gets much faster. Again, when you try to run such code, you don't have to just like take things for granted. You can also open up this model and see what is inside. So once we apply this, we get a model where LoRa is applied. Now if we try to look at in the transformer layers, we look at the first layer and its self-attention module. You can see what is happening here. We have a linear module of size 2048 by 2048, and 2 additional modules are added here, which are LoRa A and LoRa B. One is of size 2048 by 16 and other is 16. So there will be a matrix multiplication between these two, A cross B, so that you again get a 2048 by 2048 matrix. In this model, this base layer weights will be fixed, and only the LoRa A and LoRa B weights, they will be trainable. Right? So number of parameters used by a lot now. Same thing happens to key value and out projection. So when you are trying to create this LoRa model, you can specify which all layers you want to do the LoRa for. Here it is provided that we want to do it for query, key, value and out projection. We also want to do for gate, up and down projection, which means we are trying to modify this layer as well, attention layer here. There are other parameters like you can change the rank. There is LoRa alpha. You can play with these values and see which works best for your experiments. Similarly, we can see in the MLP also, we have the same thing. Okay, till this point, any questions, any doubts? Yeah.
LoRa adaptation when you break that big text into smaller for the value, and that is what is listed in that base. Right? So if I don't want
Yes, yes. So the question is that what if I don't want to apply LoRa for a particular layer or even a component in that layer? Like for example here, Q projection is just a component in the attention layer. And let us say you don't want to apply LoRa to that. You just remove it from the target modules and there will be no LoRa A, LoRa B components for that particular module. Yeah. So that will definitely reduce the number of parameters you need to do. There is also something called Q-LoRa, right, which is quantized version of the low rank adaptation. There is a small difference between LoRa and Q-LoRa is that in the Q-LoRa version, all the weights which are frozen, we try to quantize them. You might have seen that when you do the training, your weights are in float 32. But when you do the Q-LoRa, your weights can be taken to even 4-bit, right? So previously, I think one or 2 years back, 16-bit was famous, then 8-bit, and nowadays we are able to do good kind of performance even with 4-bit. So what happens is you try to compress all these weights into 4-bit, and on the fly you try to decompress it because compute is faster. Memory is the main problem in the LoRa fine tuning, because when you are trying to bits which you are not going to, or like you are not going to change them, right? So there is no point saving them, like there is no point they consume a lot of memory in your GPU. So that's why they used a quantized version of these weights which gets dequantized on the fly and then gets quantized again. Okay, now we will see one particular data set. This data sets library is also maintained by Hugging Face, so you can play with and you can load many different kind of data sets which are available. You can also specify a split like this. Just like if you are just trying to play with a data set, you don't want to load the entire data set, right? Because that will take a lot of time when you are not intending to train on the entire data set. Here we are just loading 1% of data which has just 1000 entries. How the data set looks like is like this. Okay, we have to load the data. It's saved in the Parquet format. Have you heard of the Parquet format? Yeah. Okay. So I've just seen in my experiments that if you try to save your data frame also in the Parquet format, it was much faster to save and load back. Right? So it might just become handy if you want to try. Like generally we save it as a, right? Save it as a Parquet format. It's much faster to save and load back. This is only relevant like if you are dealing with a very big data sets. For small data frames, it works just fine. Okay, So data sample looks like this. From human and then value. So value is specifying that what does human say, and then from GPT, which means what a model says. So there could be a prompt here which is given by human, and then GPT tries to generate the response to that prompt. Now Unsloth provides something called as standardized shared GPT, which, like, once we apply this, our dataset gets converted into a standardized format. Because when you work with these datasets, each of them, they will be like available in different format, which means that sometimes you may find instead of GPT there is a model here. Sometimes instead of human there is a user here, right? So because of these inconsistencies, we can use this shared GPT, standardized shared GPT format to make it into a consistent format. So now you can see that we have role as user and content has all the text. It also applied another transformation which converted that text to this particular format, where it starts with a specific token and then it tries to specify like who is generating this text which is coming now. Right? So start header ID, then it says system, which means this is a system prompt. Then there is a user and we specify what is a user prompt, and then at the end we will have a model or assistant. Right? So role is assistant here. You will see that when you use different models like Llama or Quen, these tokens change for each and every model. So that's why all the models also come up with like when you load it with the Hugging Face, you also get this standard template along with them. So you can apply and get try to convert it into this format. Okay, so once we have it in this format, we can simply go to the training. We provide model, tokenizer and dataset. We provide maximum sequence length which you want to use. We provide some additional training arguments, and then we start training. So this has just created a trainer object. We have to start training yet. Now there is a feature which Unsloth provides which says train on responses only. Now what does this mean is that when you are trying to fine tune or train a instruct model, like which is not, you want to only compute your loss for the assistant's response, right? Because let us say you have given a very big prompt and then there is a very big answer to that prompt. You don't really want to compute loss for your prompt because that is given by you. If the model is able to predict it well, there is no benefit as such. So we want to only compute the loss for the response part, and to enable that we can apply this function train on responses only, and it will enable that behavior that loss will only be computed for the responses. We can see how that has worked out here. We have just applied this special character for everything which was before the response. So you can see that all these characters just became at the rate, and the response only starts when the model starts predicting its response. Okay. So at this point we can see what is the memory consumption and we can kick off the training. Here it shows what is the total number of trainable parameters, and you can see it is just 1% of the overall number of parameters you have. The model has started training, and after 5 epochs the training will end. We can see after training what is the peak memory. This will give us an idea that when we train this particular model, how much GPU memory it will consume. Based on this, you can play with different parameters like the rank of your LoRa. Right? That will also change this behavior, that like how much memory your model will take on the GPU. Okay, once the model is trained, we can just do the inference. We can provide any prompt to it and get the answer. So we asked a question, continue the Fibonacci sequence 1, 1, 2, 3, 5, 8. Now sometimes you might provide a very big prompt and your model generates a very big answer. So sometimes it doesn't make sense to just keep waiting while your model generates the entire response. Like how it happens in ChatGPT, right? ChatGPT starts generating something, and if you don't like it, you just stop it in between. You say that, okay, you are doing something which I don't want. So you just stop it there. Similarly, we can use this template which is provided here to get the same behavior. So now you can see that as it was generating the tokens, it starts showing the output directly. Now once you have trained the model, you can just save it using this syntax and you can load it back. We are just asking a question, who came first, chicken or egg? Give one word answer. It stopped after one word. Okay, so yeah, I think we have covered the content for today. We still have some time. So if you have some questions on today's session, we can take them. You mean train on responses only, that part?
Yeah.
Yeah, so we are masking them so that we don't compute losses for them. So they are only masked at the output, not at the input. So when your model is trying to generate something, it will still generate everything, but it will not compute the loss for the system part and the instruction part. Because there is no benefit of correctly generating the prompt that I as a human is providing. Right? There is only benefit, it is able to generate the answer correctly. I think in the simple terms, we can say in that format that if you are providing it a question and answer, there is no benefit of generating the question correctly. Right? So if you are generating the answer correctly, that is helpful. And people saw that when they tried to generate the question also versus they just generate the answer generation provided them better performance. So when you
have to fix the options every time we do this.
Every time as in?
Like for all purposes, we have to mask the question, or is there some use cases where we don't mask the question?
Generally, it is found, like this is a recent finding, like by researchers, that if you use this, it provides better performance. For your data set, you may find that it is not adding much value, or you may see there is a huge gap in the difference. Right? Again, the no free lunch theorem. Yeah.
Yeah, so for fine tuning, there are several alternatives to LoRa's, like LoRa plus, Dora, many others. So which one to consider one? How to decide which one to use? And also, uh, which one to consider between LoRa and QLoRa?
Okay. So I think if memory is not the constraint, you can go for LoRa. You don't have to do QLoRa, because when you do QLoRa, there is going to be some hit on your performance. Because you are quantizing, and during the quantization, some information is always lost. Though we are trying to like preserve maximum information, but when you like go from 32-bit to 4-bit, some information is always lost. So if you have enough compute, your GPU memory is not getting like out of memory, your model is fitting well enough into your model, then it's okay. And the other point of using QLoRa might be speed also. It might provide you better speed compared to LoRa. In those cases also you can use QLoRa. There is also something called as Dora. I think that is used when you don't want to do the low rank adaptation. You want to use a full rank matrix which is added to the weights, but it is like there is a better conditioning which is provided to this matrix so that your model provides better performance. So I think you can play with these three techniques and see which suits your application.
So my question is very specific to Unsloth,
Okay.
which was actually not discussed here, but I think it falls on this realm. Is that when we load the model, by default, Unsloth is loading it in 4-bit,
Okay.
right? I think that is generally how the template code comes up. We may
Yeah.
decide not to load in 4-bit, but I think most of them are load in 4-bit is true.
Yes. So here if we
Okay,
provide
here
false,
it is false. Okay.
Yeah.
So anyway, so if we are loading it in 4-bit, so basically we are doing that so that it consumes lesser memory, lesser VRAM, right?
Right.
Okay, so now if I fine tune it,
Okay.
right? Suppose my job is done and now I want to save this model.
Okay.
Unsloth by itself provides a save option, model save option.
Okay.
And now in that I don't do any quantization.
Okay.
Now, although the default model was 4-bit,
Okay.
am I, the question is, am I actually saving it again in 16-bit if I don't quantize? So do I have to quantize it again? That's my question. It's a little confusing because you did your task of fine tuning or whatever, and now you're saving it. So by default, are we again saving it in 16-bit? In that case, we are not maximizing on, like we should again quantize it, or should we not? That's the question.
Okay. Okay. So the question is that when Unsloth is saving the model, is it by default quantizing it or not? Right. So I'm not sure like what is the default behavior, but I'm sure they would have some resources showing that if you want to quantize any model into 4-bit and then save it, how to do that. So that there must be some resources on their documentation of how to do this. And I don't think it might be happening by default, because you might be seeing that whenever a new model comes up, let us say Gamma 3 came, within 12 to 16 hours, Unsloth teams, they try to upload the default models first, and then they also upload these BNB 4-bit models which are there. So I think they are going through some process to first quantize them and then upload. Yeah. There are benefits of quantizing it, which are like, if your model is taking, let us say 50 GB of memory, and then once you quantize it, it becomes just 10 GB. So when you upload and download this model, it's also beneficial, because downloading 50 GB chunk and uploading it back is not a joke, right? So when it is much smaller size, is useful. Any other questions? Yeah.
More parameter of maximum sequence length, right?
Right.
Right. So suppose now I have a fine-tuned data, not like the data that I want the model to be fine-tuned on, and now if I determine the maximum sequence, I can use a tokenizer and then I determine that, and I know that it is some number, say 3000, right?
Right.
Depending on that, should I necessarily change this number, or if
I think generally it is advisable that you like determine some number which you know that it is not going to be exceeded, and then use that particular value. I think this is a bit on like trial and error. You have to check. Yeah. Okay. So if there are more questions, we can wrap up the session. Yeah, there is a question there.
You say the use of NVIDIA SMI in the
Okay.
Google Colab.
Okay.
So it's directly run on Google Colab, or we install anything dependency.
It is by default installed in Google Colab.
But in my system not working.
Like what you are trying to type in your cell. If you directly type NVIDIA SMI, it will not work because it is a Linux command. So you have to use this NVIDIA SMI. So then it will show you the memory. So in Google Colab, whenever you want to do something which is like a Linux command, you always have to use this exclamation mark. Okay. It is also used in pip install. You might have used, like when you do pip install, you always have to use this. Okay, so with that we end today's sessions.